Is there anybody in the room who does not know what this is?
It's a whiteboard.
No. The symbol.
Bends in a river.
Okay, I guess she, that's okay.
Mississippi River actually.
All right, this is an electronic symbol for a resistor. And if you normally look at a schematic, you would have symbols connected with wires, and the wires are assumed to have no resistance. So you use this to indicate a specific amount of resistance. So if we have this resistance, and we apply a source, like a battery for power, what's this, nice? This will be as shown in figure 2 of your handout. The current flowing through that resistor, I presume everybody knows what current is, has some idea, is determined by Ohm's law. And you can see in figure 2, there are the 3 expressions for Ohm's law. Now, if you apply too high a voltage, the current may be too high, and what happens when you put too much current through a resistor?
It goes up and
Smoke. Smoke happens. So we understand that relationship with what's called the power formula, and that's shown in figure 3. And again, I've shown it solved in all 3 variables. So this is a fairly simple thing, right? The math is not too complicated. There's no advanced calculus involved. Now, being retired, I like to build little circuits and things, and I like to make measurements. This is a typical example of stuff I built. Now, those are resistors.
They let you carry that in an airplane?
This is a USB load. So I can have a 1 watt load, a 1 amp load, a 2 amp load. This is a 1/4 amp load, and that's a 2 amp load. Those little power cubes you've got in the handle, those are 2.1 amperes, so that's a 2 amp load. If I wanted to test that, I could use this to test it. But if you look at this, you can't see it, but the resistors are connected in what's called series or parallel. And I have 100 such devices that I built for various purposes. We've actually had a programming contest some years ago where it was primarily an interface thing where if you look at combining the Ohm's law and the power formulas together in figure 4, we have the famous Ohm's Law Wheel. So that if you look, R-I-P-E, R for resistance, I for current, P for power, and E for electromotive force, or as measured in volts. So if I know, if I want to calculate power, I can see that I can calculate it in terms of E squared over R, voltage times current, resistance, where am I going? I can't even read that. That's
I squared R.
Yeah.
oh, okay. Oh, my eyes, I can't see that little 2 up there. Okay. And of course, our contest was given any 2, calculate the remaining 2. Okay, now, if I take 2 resistors, and I put them in parallel, as shown in figure 5, we can calculate the equivalent resistance. And the Req, shown in figure 5, is equal to the well-known product over the sum. No problem. Now suppose that the resistors have specific values. R1, say, is 80 ohms. And because a resistor has another very important rating to it, it has a power rating, and you should not exceed the power rating. So the resistor we're going to use here, say, has a power rating of 1 watt. So R2 will be 120 ohms, let's say, and it has a power rating of 2 watts. So we can use our textbook, first semester electronics, calculate the power of the sum, and what do we get? Anybody got a calculator? What's the number here?
I have 48.
Hmm?
Yes, I- 48.
So we have 80 times 120 divided by the sum,
200.
48.
200. Right. What do we got?
48.
Hmm?
48.
48? Really? Well, it's got to be less than 80, right?
Yeah.
Okay, Joseph says it's 48, I'll take his word for it. Now, the question is, what is that effective power? We have this equivalent resistance, and it has a resistor that has a rating of 1 watt, and another resistor has a rating of 2 watts. What is the effective power of the combination?
What's the voltage?
Does it matter?
Well, you want the maximum voltage before one of them goes up in smoke.
When I run across this, and because you see my example here, I mount resistors up, and I have these resistors, and I need to show what the resistor is. I got all these resistors connected. What are they? All right. And then I realized the solution to that problem is not normally discussed in the textbooks. And that applies to whether you have 2 or more resistors in series as well. And that was the first revelation. A simple, basic problem, and the textbooks don't cover it. So I got in touch with Roger and said, Roger, do you teach it? What did you say, Roger?
Well, yeah, we don't usually, we often have them calculate the power dissipated by each resistor without assuming there was a rating.
Well, yeah,
But
you
we
got
don't
yeah.
say, if each one if you have some fancy circuit and each one has some maximum power rating, what's the maximum power rating of the whole thing? We never done that.
Okay, that's the answer I wanted. Okay, so that was the first revelation. Not too,
Well, I think it's
not too exciting, not too revolutionary, but
Yeah.
over.
then I went over the parallel combination, and then the revelation was in figure 6 that the effective power of a combination of resistors cannot be calculated. You have to go through a process first. And the process consists of 4 steps. Step 1, you determine the limiting resistor of the combination. In our parallel case, the limiting resistor is always the lowest valued resistor. In a series case,
For a parallel case, yeah. Well,
it's the highest value. Okay. Step 2, You then calculate the voltage or current as determined by the limiting resistor. So in a parallel case, it's going to be the lowest resistance. And so if we know the lowest resistance is going to be 80 ohms, and the power is 1 watt. We want to know what the voltage is. We look over at figure 4. The voltage is equal to the square root of the power in the resistance. So step number 2 is we calculate the E equivalent in the parallel case. And once we know what that voltage is, now what we're saying here is we're going to increase the voltage across this combination until we get the 1 watt. That's it. Now this resistor is higher, and so it's going to be dissipating less.
So it'll also stand 2 watts.
So once you know that voltage, you can figure what the power is knowing the voltage and resistance of this one. And finally, the last step here is you add those 2 powers. So the revelation is here, there's no formula or equation that we can derive that we can simply put in those values and get it. I suppose maybe you could. That's a good problem for you, Roger. Derive a, but you see, you have to make a decision and you have to know something. What is the lowest valued resistor in the parallel combination or the highest valued resistor in the series combination?
Now, if the 80 ohm resistor were rated at 2 watts and the 120 ohm were rated at 1 watt,
Yes.
then the right hand, R2 would be the limiting one because it would go up in smoke probably before the
I love
R1.
this. Oh, this is good. Roger, say no more. You'll destroy my total opinion of you after 4 years.
well,
I'll destroy it worse than Roger. You're assuming here that R1 and R2 are not in thermal contact. They have to be totally thermally isolated.
we're assuming
because
they're
the
in
heat
there.
from one will warm up the weakest link and
Okay.
make it weaker.
All right, Richard, you and I have discussed this. Let me say this is a theoretical problem discussion.
Ideal.
Because when we get into the second revelation, there will be 10 dozen practical arguments, and we don't want to get into all those. Okay? We're going to assume that both of these are run air, both of them are going to dissipate the power in the manner so defined by the manufacturer who says, I'm going to rate this at 1 watt, I'm going to rate this at 2 watts. Okay? So that's the first point, first revelation. Now the problem. Now, Roger, have you caught up to me here now?
Yeah, okay.
Good. This is all driven by a practical, real problem. And if you look at figure 7 here, you'll see a little gadget, and I get a newsletter from an outfit called MPJA. Merlin P. Jones Associates, this little sound level indicator. I see this in their little flyer. I said, that's an interesting little thing to play with. And I know that I'm not strange because Jim does this all the time himself. He buys things to play with them, right? And what struck me about this little LED array was the fact, one, it had the diode bridge part of it, it had the limiting resistors as part of it, and it was about the size of, a silver dollar. And I thought, this would make a nice replacement for a microscope mirror. You know, a classical microscope, you need light, and they have a mirror down below the stage, and you adjust it to get the light up through the microscope. But the microscopes that I use are USB microscopes, and they have a video camera, and a video camera has sophisticated electronics to adjust the voltages on the camera to get the image. So if I'm going to be fiddling with the light, I need to have good control of the light. So let's look over to figure 8. One way to control the light is to add resistance. If I add high enough, the current is so low that the light is off or zero. If I lower the resistance, it gets brighter, and I can control my brightness and my little LED array. Now there's two ways I connect a variable resistor, and now we've jumped from a fixed resistor to a variable resistor, and now we're going to get a little bit, in fact a lot more complicated. I'm going to pass this around so you can physically see the mechanical implementation of what is called a potentiometer or variable resistor. I bought a medium-sized one so we can handle it. If you look at figure 9, you see that the pot has 3 terminals, and here's the 3 terminals, and there's a wiper arm here. And I don't have a big knob on here, but you put a knob on there and you turn this around. And this particular resistor is made up of nichrome wire, and it makes a physical contact so that as I move this around, the resistance of one goes up, the other one goes down. Okay? And as I've shown here in figure 8, I can connect it as a rheostat, which is a 2-terminal variable resistor, as shown in either the left or the right. You would normally want to use the one on the right for 2 basic reasons. One, that unconnected, which NC means no connection. The unconnected terminal is sitting there hanging in space. What does that mean? It's a small antenna, and that is a potential source of noise into the circuit. And the second reason is that since we have a spring-loaded wiper arm, that if I bang this arm may bounce and momentarily break the circuit. Now, in some circuits, if you go open, it can be very disastrous. So you can see the connection where it says better there. If that wiper arm, that arrow, breaks the circuit, you will always have that amount of resistance in the circuit. So if it's a 100 ohm pot, you will always have at least 100 ohms.
The load is in this right-hand wire here, isn't it? You're not shorting out the bottom lower half of it.
What figure?
In figure 8.
Figure 8.
In the right-hand part of figure 8, isn't the load in that right-hand wire underneath the arrow?
No.
I
See,
mean, you've got it shorting out half.
figure
the
8, left and right, are the same pot, but connected in 2 different ways, both of which function exactly the same to give you a variable amount of resistance between the 2 terminals.
Oh, okay, so you're deliberately shorting out the lower half of it.
Yes, and for the 2 reasons I just gave you.
Okay, yeah.
Okay? You pass this down.
I see, yeah, okay. Yeah.
By the way, the one I just gave Jeremy, that's what might be considered a high-powered pot. That would be about $44 if you had to buy it.
Where's the
All right.
smoke? Where's the smoke?
Huh?
I was trying to find the smoke.
It's still in there.
Yeah. The smoke. The smoke capsule.
What?
The smoke.
No, let me assure you that any resistor on the planet can smoke. You put enough voltage across it, it'll smoke. Now, the reason that I became concerned with the pot is that I wanted to be able to vary the brightness of my LED from off or 0 to full maximum. So what I do is I connect that pot across my 12 volt source, which the 12 volts is what the LED is designed for. And the wiper arm is at the arrow, and the resistor across the wiper arm is what's called the load. And as you move that up and down, R1 becomes 0 if you're at what I would consider full maximum, or 100%. And usually you want that to be clockwise, so that you turn it clockwise, the lights get brighter. And if you go down counterclockwise, you go all the way down to the bottom, there's 0 voltage across R3, and the light is out. Connecting this, as shown in figure 9, is called a voltage divider. And the variable resistor is called a potentiometer. All right, let's go on to the next page. This voltage divider circuit you'll find in all the textbooks. You go on the internet, and along with that voltage divider, they're going to give you the equation, and usually what's of interest is the output voltage of the wiper arm or across the load. And figure 10 gives that classical V out equation. V out is equal to V in times the R2 resistance divided by the R1 resistance times the R2 divided by the R3 plus 1 plus R2. Now we're getting a little bit more complicated, but it's not high-level math. So my question is, what is the power dissipated by the pot? And of course, if you look at that, you say, well, it's the sum of the power of R1 plus the power of R2. That's what I want to calculate. So off I go to the textbooks, I go to the internet, and lo and behold, nobody does that. Nobody tells you how to do that. Nobody explains that. Now, isn't this a little strange that 100 years of electronics and something, a simple little thing, isn't discussed? I'm not saying it isn't discussed by anywhere, anytime, by anyone. I'm just saying that my limited ability to look through my library and look on my computer using Bob's internet search techniques is I don't find it. So, I decided to investigate. And in the process of investigating, I run into a little bit of a problem. My math skills are a bit rusty. I'm not sure I can just whip this out. So, with the assistance of an algebraic program to help do my algebra for me, I go through and I derive an equation that will give me and calculate for me the power dissipated by the pot. Okay? And figure 11 is a result of that sweat, blood, and tears and about 5 pieces of paper, and Roger's blood, sweat, and tears, and his pieces of paper. And as Roger says, you know, this is messy. Perfect word. It's messy.
I don't know, figure 11.
Figure 11. Now,
Where is figure 11?
You have a defective handout.
page 2, right-hand box.
It's on the back of page
Oh,
1.
oh, I have no, okay.
Are you blank?
Page
Oh.
1 is blank.
How many?
I've got a power problem. in
Eric, you have,
You're down there.
okay, sorry. I did make, I'm sorry, I did make these copies. I apologize if I didn't catch the blank one.
Roger.
Now, Since I wasn't sure of my math, I've had a couple of people check this equation, and I'm pretty well convinced that that equation is correct. Now look at that equation. What it's saying is that if you know your input voltage, you know the pot resistance, and you know the load, you can calculate the power of the pot. Great. So what did I do is I wrote a 48 program to solve this equation, and I put in some values. And after about 4 hours of calculating,
4 hours.
at least, I made a table, and I didn't include the table.
You should have used a calculator.
No, I didn't the calculator. I used the program. The thumb drive has my paper. It has all these gory details, all the tables and the numbers, and I came to a conclusion. You can't calculate the power of the pot. And that was revelation number 2.
What?
And again, it wasn't in the textbooks. Why can't you calculate the power of the pot? Because the power dissipated by the pot will be determined by, I didn't draw it, but you look in figure 10, where is the position of the wiper arm?
Of course.
Okay? Which you can intuitively kind of guess that that's the case. So, pots are a marvelous device because it allows you as a user to interface with the circuit and control the circuit. You turn the knob on your way to work, you're listening to the news, you turn up the radio because the street noise is too loud or whatever. Okay? So I calculate, 10 degrees, or 10%, 10, 20, 30, 40, 60, 70, 80, 90, and between 70 and 80, they're almost the same. Oh. So I go 71, 72, 73, 73. Oh, there is a position in which the power is a peak. That's the power I want. I don't want to exceed that. One reason would be that since I'm the designer of the circuit, and I have no control where the user is going to do it. The user can turn that any way they want. Suppose they park it at the peak power and leave it there.
The current, and then from there, what we calculated with the
I just
power.
gave you the equation and other stuff, and you came up with a spreadsheet.
I came out with I derived another equation, but it calculated the current iteratively and then calculated the power or whatever.
Okay.
And
And
then,
then we revised it with a second version. Okay? But
yeah.
the mere spreadsheet that he sent me, which had a VBA,
macro, yeah.
macro embedded, certainly not beyond my capability, okay? And, what took me 4 hours to make a table of values, bang, there they are to all the decimal places you want. Great. So now this revelation was, the power of the pot is determined by the position of the pot. The power of the pot peaks at a certain position, and that would be the power that I would need to know. I want to know what is the power of the pot. Why? Because the cheapest pot you can buy, they'll give you two numbers. The pot value, 100K or 10K or 1K ohms, and the wattage. Cheap pots, Chinese pots, they give you nothing else. But if you buy a good quality pot, especially one used for instrumentation, $10, $15, that's not unusual. And you got 9 yards of specifications. One of them is what's called the step-on, step-off. In other words, I got this wiper here, and when I get up to 99%, I slide off of the resistive element, and I go onto a solid contact for 0 ohms. All right? Now, I told you I didn't want to get too much practical stuff, on pots and resistors, because this is not an engineering class. But a normal single-turn pot, and we know one turn is 360 degrees, is about 300 degrees. The normal resolution of that pot is about 1%.
By email.
Okay? So, in terms of practical values, 1 to 99 is, I'm concerned. You get near the edge ends, and John, who was going to cover his analysis of the circuit,
Not enough views.
whenever I find something that doesn't quite click with the rest of the world, I start getting worried that I'm the one who doesn't understand. So I asked, Roger and Amir and John did a very good job. His description and analysis is also on the thumb drive.
I thought we corrected figure 11, which has too many V's in the first term and not enough V's in the second term, so the units aren't right.
Well, what I did, people kept saying units. I said, well, I'm not worried about units. I'm worried that this is correct. And my
Well,
measurements say it's correct, so.
But I mean, if it's eventually wrong, you know it's not gonna be correct.
Yeah, well, John confirmed my equation that that equation is correct. I wish he was here, and you can hear him say it. My whole discussion assumes my equation is correct. So, when you leave here, Roger,
Equation is
and
correct.
you prove my equation is wrong, let me know, I'll tell the world I made a mistake. Because there's a whole lot more data I have that seems to suggest my equation is correct.
Okay, I see two problems with this analysis so far.
Okay?
The first problem is that by telling us that the load is a resistor, you misled us.
No, we've been over this, Richard. Forget that.
Okay.
Assume that my LED, he's saying, oh, this is an LED, this is a silicon junction, the voltage and current are not, linear, and all that stuff.
Okay. The second problem is that you're assuming that all the heat generated in the pot
Again,
is uniformly distributed throughout the pot, and it's not. The heat is concentrated in the upper segment of the
It
pot.
may be, yes.
Where,
Yeah, that's true,
and,
yeah,
and
that's
by
what it is.
concentrating the heat all in the upper segment, you may overheat it and burn
Okay.
it out.
Again, like we did with this parallel
It has a
situation,
superconducting-
But the
we
equations are
have
correct.
to consider that when two resistors are involved, that one resistor may be a limitation. So what you do is you say, the pot is, say, 1,000 ohms, and the power is a half watt. That's a good typical pot. So you calculate the current using our little set of formulas, and that current must not be exceeded.
Yes,
So when we worry about what you're saying,
it's the
we
total
have-
current.
yes, but again, the number one part of the revelation is that it's a variable thing. Okay? So using my equation of questionable correctness by some people, we go over to figure 12, and we take a 2K pot with a 2K load and a 12-volt supply, and I calculate the power versus the rotation. And figure 12 shows that, and it shows a peak. Now, how sharp that peak is, where that peak is located, this is all going to be dependent upon the load. And let me get into that in a moment. Let me redraw that figure.
It's going on back there.
This is called the load, R sub L. This is the input voltage. When you do go to the references and you look up pots, here's what they tell you. they tell you that as I move this up and down, the voltage will go from the supply voltage to 0 voltage. Normally the pot applications that you all experience every day are for signals, low currents. And there's a relationship that the engineer wants you to have with the rotation. In other words, if you rotate it halfway, you would normally expect that this would be half the voltage. You rotate it 25%, it's going to be 3/4 of the voltage, etc. Now, I don't want to get into pots again. Richard would love to go off the deep end on pots, but there's a thing called the taper on a pot, which is as you rotate, the resistance may change not linearly. The one I passed around, it would be a linear pot, but it might change in a logarithmic fashion. And the reason for that is that your ear response, compared to the electrical response, is non-linear. So that roughly to your ear, if you're halfway, it should be, so I say halfway from 0, it should be half the maximum volume.
And eyes also respond the same way. Logarithmically.
Oh yeah, but let's not get off the deep end on that, okay? So, when they talk about pots, they talk about that, they talk about the taper and how the load affects the taper, etc., etc. And then they'll always say that RL, for the pot to work properly, should always be at least 10 times higher than the value of the pot.
Yeah, for
That's,
linear voltage.
that's the takeaway. That's what all the textbooks say. But they don't answer the question, what's the power being dissipated by the pot? They're always concerned about the rotation, the linearity, all that stuff. I don't care with my little LED array. I just want to turn it around and adjust the brightness. I don't care if it's linear. Oh, they do say one more thing. If you make the resistance load lower than 10 times, you are going to be very wasteful of power. So if you are going to control a circuit with a potentiometer, if you have any kind of a substantial amount of current or voltages involved, it's going to be wasteful of power. Obviously, putting the source across here, you have a constant power going, potentially dissipated by the pot, and then you put a lower resistor here, that's even more. So, what I did was to make a series of calculations. Each time, when I say the power of the pot, I want the peak power. And I came up with the plot shown in figure 13. Now again, the 19-page paper on the thumb drive gets into more detail. And what I did is I tried to show all of the relationships involved. I want to show how does a load value affect it, the power, and the position of the rotation. And so we have a curve. Oh, one more little tidbit. Going back to figure 12. You'll notice that okay. Down near the very, what is it, I don't have my glasses, 10, 20%, the pot power doesn't change much. But you'll notice that up here at the 79% of rotation, 79% of maximum, it was a peak. So one of the questions I wanted to know is, does that peak move around? And sure enough, it does. And from calculating many cases, not doing a theoretical mathematical analysis as Joseph could probably do if he was so inclined, or Roger, or some others in here maybe, I came to the conclusion that the peak always occurs, and this is a guess, but I'm sure I'm within a few percent, from 74.5% to 99%.
That's what I found also.
Okay, Roger confirmed. Now here's the question. Oh, I'll wait till my conclusion, because that question is in the conclusion. So I come up with the curve of figure 13. Now, what I'm showing here is the ratio of the load value divided by the pot value. So if we look at the red 1 here at figure 13, if the load in the pot is the same, if it's 10 times more than that, as all the textbooks would suggest, or if it's 100 times, no big deal. It's a flat horizontal line and the power is practically zero. But if we decrease the load, the power increases. Notice this curve starts to rise up, and when we get to where the load is 1/10 the value of the pot, it's not seriously rising very much. In fact,
Not linear.
you can go up to up to a 1/100th of the pot value, and it's not gone crazy. Beyond that, whoop, smoke time. So that was another part of the revelation.
Question. In figure 13, what is actually plotted? Is it the load to pot ratio?
Yes.
Or is it the power in watts?
Well, the power in watts on the y-axis and the rotation on
Slider position is.
x-axis,
It should be a,
and I'm plotting the various load values. I'm trying to combine 3 variables into one plot.
oh, okay.
Now,
Okay, I got it.
so what might be a conclusion here?
Assuming some load.
Engineering is always a series of rules of thumb and approximations, right? I would say 0.05, in other words, the load resistance is 0.05 times the pot resistance would be
That's okay.
calm and cool value. Above that, it's going to go very high, very fast. Okay. 2 revelations and a problem. And here's my conclusion I'm going to read, if you don't mind. Whenever you ask a fairly simple question and the topic is not covered in the conventional places, textbooks, class lectures, internet, you wonder why. Perhaps you don't understand the problem, Richard thinks they don't, the math, or the method of analysis, Richard agrees. This was a case with the revelation described in this presentation. This topic is, or may be of interest because it's unusual, calculation intensive, and involves several conference attendees. Number 1, the pot power is wiper position related and peaks within a narrow range of about 74.5 of a maximum 99% of maximum. And as Richard pointed out, and I mentioned that you really also have to monitor the current, because at some point you'll exceed the current rating, and that exceeds the power specification. The issue is not well described in any of the literature we have found, we meaning John and I anyway. The pot is usually described as a voltage divider and not a current or power controller, which I am using it as, which got me into trouble in the first place. PWM, which is called pulse width modulation, is usually used for this purpose. But a pot is simpler and could be lower in cost. Number 3, the actual pot power calculation requires a search or process for its solution. Number 4, after the analysis, we noticed that the wasted power situation is not as serious as the textbooks usually imply. Loads of 0.1x of the pot value are quite practical without excessive pot dissipation. Most textbooks only discuss load values at least 10 times the pot value, with the emphasis on signal level taper preservation and voltages and currents. And number 5, knowing that the pot power is position dependent is important to know. The values involved may be critical because the user may park the pot at the peak value and leave it there. And then I have a little disclaimer. The application of pots is quite a complex subject, and there are many designs intended for a substantial number of applications. While the single-turn pot is used as an example, there are 4, 10, 20, and 22-turn pots commonly available. Even the step-on and step-off resistance are specified for quality pots. This analysis was a theoretical discussion only, and it was primarily focused on the 1% to 99% ranges of pot. John provided insight at the extremes. Curiosity question. This is a serious math question. What is the exact low value for the bottom end of the peak value? The 74.5 minimum value, is only an approximate guess based on a few calculated cases.
But I had figured 3/4, which is close to your.
Well, 75 to 100. I
75
found one that
versus
was 74.9% or something. And I have a stack of calculations and data, and I didn't have time to go back and find that value and then use that as a starting point to see, But it's an excellent math analysis kind of a question.
I think,
Do we have any questions?
yep.
Yes.
I think it's a nonlinear dynamics.
Pardon?
It reeks of nonlinear dynamics.
At least what?
It reeks of nonlinear dynamics.
Nonlinear dynamic. It reeks of it.
Reeks it, absolutely, yes.
Yeah, it's
Okay.
nonlinear equation. That's why deriving.
See, I only taught
and
physics
taking
and not
the derivative of
practical
zeros.
engineering.
Well, if anything, I got you thinking, but my point was that a standard 100-year-old simple resistive circuit is not having all the cases covered in the textbooks.
Another thing,
And I think the reasons for this is that because there is no straightforward solution,
Yeah.
and because there is no real practical need for it, the textbook writers say, well, we will just give them what they need, and that is series and parallel resistor combinations are usually done with the same valued resistors. So if I have a 10 ohm resistor, 10 watts, and parallel another 10 ohm resistor of 10 watts, I have 5 ohms. Like my little USB load is here, and clearly 10 watts, 5 ohms, and 20 watts, because they're equal. So, aside from the simplicity of calculation perspective, there's another overriding driving force, economics. If you got a bunch of resistors in a project, if you can use the same one in many places, you buy a larger number, you get them at a lower price. That's my theory of why this is not covered. It's not that engineers have not analyzed this or understood this, it's just the reality of the real world. Any more questions?
Yeah. If you wanted to really see what's going on, what instruments would you put in the circuit as far as amp meters and voltmeters? Where would you put them?
Well, I would put,
Because once you know the current and the voltage,
I'd put an amp meter here, I'd put a voltmeter here, I'd put a voltmeter here, and an amp meter here, so 2 amp meters and 2
and then
voltmeters.
you know everything, right?
Well, actually, the article I'm writing is not really finished. I only gave you the slimmed down version in the proceedings. I have a meter that I think I've shown people. We don't have power handy here, but this is a meter that every one of you should have. It's like $9, maybe 14, depending on where you buy it. It's a USB-A male. You plug it into your power cube when you're charging your phone. And you plug in your phone charger here. And then this display lights up and it gives you 4 simultaneous values. It gives you the voltage to the nearest millivolt, 5.002 volts. It gives you the current to the nearest milliamp, 0.003 amps. It gives you the power in milliwatts, again, 0.001 milliwatts. And it gives you the charge, which is current per unit time, simultaneously. So what I could do, and I have 3 of these, what I could do is put one here, my source, put one here, take a photograph.
You've got everything.
There you go. There you go.
That sounds like a thing to do.
Yeah, simple.